To extract nonlinear principal components robustly to noise, this paper uses kernel method and regularization for robustness to noise. So this paper is called exactly robust kernel principal component analysis. I will also shortly have a look at another paper which is called robust nonlinear matrix factorization for dictional learning, denoising and clustering. The second one is sort of performance speed improvement. But the first one seems to have the principle, sort of the combination of previous papers to gain sort of principle to how to do this. So it's from Jicong Fan, Tommy, W.S. Chow, Fellow, IEEE, April 17th, 2019. PCA is a component. PCA is a short for acronym for principal component analysis. What it does is that it tries to find within some data or some other matrix. It tries to find the sort of the underlying latent variables which explain variability in the data and sort of decompose the distribution of the data. So PCA is a linear method, so it looks for linear transformation which transforms the matrix such that in the new orthogonal basis it is low dimensional or approximately low dimensional. It is commonly used to reduce the number of features, reduce the dimension of the data, or explain sort of the distribution using some sort of latent features. The PCA is related to factor analysis, which is used in psychometrics. If you heard about psychometry, they are sometimes looking for these sort of underlying common sort of traits in humans. Never mind. So the principal component analysis can be done by finding singular value decomposition or again decomposition as well. It's used for dimensionality reduction, feature extraction, noise removal, and so what? So then there exists this robust PCA variant. So original PCA is not robust to noise. I think it's in a similar way in which mean value is not robust to noise. So if you have some far outliers, the PCA will be affected by those outliers and will give you worse results. And what you want to do in some robust method is you want to get some sort of similar result, but which is it works almost the same with the presence or without the presence of the noise. So here that's a robust PCA. And what kind of noise are we dealing here? So the noise here is additive noise, where you have the original matrix and then we do some plus error matrix, right? And so in this robust PCA we sort of want to find what is the error matrix and then do the PCA on the rest. And to do that, obviously, not obviously, but to be actually robust, we do regularization on the size of the error matrix, and then we look for then we minimize the rank of the rest of the matrix. The noise is in the entire paper expected to be sparse, and the regularization itself is then also used as a number of non-zero components in the error matrix. This is sometimes used for, as they mention here, noise removal, subspace clustering, and so on. And so this was robust PCA. Then the PCA is a linear method. It gives you those principal components which explain variability of most of the data, most of the variability of the data. What we sometimes would like to do is that in cases where the underlying latent factors which explain the distribution, so the underlying hidden parameters which we cannot observe, have a nonlinear relationship with the output data. For this, we cannot use ordinary PCA, but we can still do. We still have some options which are, computationally harder and so on. But we can still do something. So what we can do is that we look for nonlinear transformation, which transform this original matrix into some higher, potentially higher or very, very high number of dimensional space, and look for the lowering number of dimensions there. So for this, there is this kernel trick used. So which basically says that you can cover most of functions for nonlinear functions in certain sense by looking at some by looking at linear combination of some sort of infinite set of kind of simple functions. That infinite set of simple functions that could be, for example, polynomials, which usually have some issues. That is, for example, those are used in Taylor expansion, or we can also have a look at these RBF kernels. How is this called? I think we will see that later. Those are these Gaussian kernels combinations. Okay, so when you use this kernel trick, so in the higher dimension, then you can do some linear operations there. All right. But again, this kernel PCA is not robust to sparse noise, and RPCA is robust to sparse noise, but it's not, it's not this nonlinear. So what we would like to do is to combine these two approaches, and that's what they've done in this paper. So they propose a novel method called robust kernel principal component analysis to handle nonlinear data and sparse noises simultaneously. This RKPCA assumes that nonlinear transformation of the data matrix is of low rank, which is different from low rank assumption of the data matrix itself in RPCA. Yes, so they look for nonlinear transformation such that resulting data matrix is low rank, and as well they look for this error matrix, which needs to be sufficiently small. So one more thing regarding this nonlinearity. If the relationship is nonlinear, then your resulting matrix can be of high dimension. So it won't help doing PCA there, actually. You really need to find that nonlinear function from that high dimensional space where the matrix can be decomposed. So methodology. So they started with looking at RPCA. So we have this data matrix, which is the sum of x, which is the actual data, plus some error, which is sparse error matrix. Sparse noise is randomly distributed. So they want to recover x and e, and this is the RPCA. This is this. This is this linear variant which is robust, and the loss function is so they try to find this x such that it has minimal rank, and plus the regularization, they want to find this error matrix which has very small number of non-zero elements. This is this zero norm. This problem is NP hard, but you can do some heuristics. Yeah, so the minimization of this rank is simplified to the nuclear norm of X and this sparse. So they approximated by this different norm, L1 norm of E, to simplify. And this nuclear norm, they didn't have it here, but I think that's the sum of the singular, the absolute values of singular values, I think. Oh, okay, so they, to continue to get this robust kernel PCA, they make this assumption that the data matrix is a function, is a result of applying function to some latent matrix, which consists of uncorrelated variables. And so this is the, and the function is nonlinear smooth mapping. They need the mapping to be smooth. If it's not smooth, I think the proofs they have here wouldn't work, but potentially there could be some other way how to do it. Okay, so they have this. In addition, the dimension of the manifold defined by f is r. Yeah, so the z values lie on some, a nonlinear plane, sometimes called manifold. They have this example picture. So in the resulting matrix, they have these sort of points widely distributed. When they do RPCA, they get some linear plane as a result, right? But the problem is that the data, which is in blue, is nonlinear. But instead, if they do this RKPCA, they actually remove the noise and get the right points. They have this another condition. This is required for this method to work. It's no sparse component addition, which says that the actual data is not sparse, and which means that it can be recovered. That the signal is strong enough compared to the sparse noise. That's what they say. So any of the latent variables, if it's prevented to be too sparse by saying that the probability of that latent variable resulting to zero or being a non-zero value is high enough. So that's the requirement. So under these assumptions, they can perform this operation. So the problem they are looking for is that the loss function is that they look for a minimal latent dimension of x plus lambda sparse norm of the error matrix, where the data matrix is decomposed into sum of x plus error matrix. And so the part of the proof that I've read here is performed by taking so they know that there is this f function, and they look for a sort of inversion of this f function, but it doesn't have to be exact inversion. It just needs to be up to linear transformation inversion. And they use Taylor expansion in this proof of this sort of inverted operation, from z through the f nonlinear function of the original data, and then I apply on this function that I'm looking for. they do Taylor expansion, saying if we are sufficiently close to the original function, we can do this expansion, and then if the rest of the expansion can be very well approximated by t terms, if we are sort of close up to linear combination, then this gives us the low rank. Then we will get the low rank approximation. This phi operation, which is the inverse f, is exactly the low rank when Taylor residuals vanish. Okay, this part is about it deals with the I think this one deals with the simplifying of the minimization function. Then they look at this radial basis function. That's it. This RBF kernel. They explain how the RBF kernel is related to the Taylor expansion. So they say here that the x equals f of z can be approximated by Taylor expansion. The features given by radial basis function kernel are also Taylor features of the latent variable z. Meaning that you can, I think what they basically say is that you can decompose this radial basis function into Taylor expansion, and then you get these yes, okay. And they simplify the loss function to this k square root plus lambda plus L1 norm of error matrix, where the k matrix here is is this radial basis function variables, I think. We take the f in x and y, and we do the dot product, and we get the components of the k matrix, which is then used for this trace here. Okay, then the proof follows from this. I haven't dug deeper. I'll skip this part. Okay, so let's go towards the end. I think they have results there as well. Okay, so this data matrix can be many different values, but they studied in particular images as they can be visualized, so they're sort of attractive, and you can as well easily see the problems in them. So for example, here they took MNIST, then they took this picture of people, I don't remember the name of this data set, and then picture of images. So in the MNIST on the top, they had the data set, they had the full data set without noise, then did the sparse noise on it, or they did some occlusions in the data, and they show that their result is better than than the previous approaches. So they say that images recovered by RPCA and RKPCA in each rows are and the original and noisy images. They show that their RKPCA approach is better. Also look at this clustering. Okay, conclusion. Recovering corrupted high full rank matrix is a challenge issue to existing matrix coupling method, including RPCA. We derived and proposed RKPCA method to solve the problem. In this paper, we included important theoretical proof showing the superiority of RKPCA over RPCA theoretically. This paper shows RKPCA to date is the only unsupervised nonlinear method that exhibits some robustness as sparse noises. We also proposed two non-convex algorithms, ADM, BTSL, to solve the challenging optimization of RKPCA. The convergence proof are also included. It is interesting to note that PL-ADSS is more computationally efficient than LDMM plus BTLS. Throughout the comparative studies showed that the RKPCA significantly outperformed PCA, KPCA, RPCA, SSCA, NLRR, and RKLRS in noise removal, subspace clustering, and or motion segmentation. Okay, next paper, just shortly. So this one is called Robust Nonlinear Matrix Factorization for Dictionary Learning, Denoising and Clustering from Jicong Fan, Chegrun Yang, Madchek. Is it Jicong Fan is the author on both papers. So this new paper is from 2020. So what they say in this paper, so this paper is basically improvement on the previous paper where they reduced the computational requirements for the method, but I think the idea is rather similar. So nonlinear methods in the abstract, they write nonlinear method fail in presence of noise or outliers. In this work, we propose a new robust nonlinear factorization method called robust nonlinear matrix factorization. Robust nonlinear matrix factorization constructs a dictionary for the data space by factoring a kernelized feature space. A noisy matrix can then be decomposed as a sum of sparse noise and clean data matrix that lies in low-dimension nonlinear manifold. RNLMF is robust to noise and outliers and scales to matrices with thousands of rows and columns. Empirically, RNMF achieves noticeable improvements over baseline methods in denoising and clustering. Okay, so here they compare it to the previous paper. In 19, which is the previous paper, a robust kernel PCA, RKPCA, was proposed to remove sparse noise from nonlinear data. The space and time complexities of the naive algorithms are ON squared and ON to the third power, respectively, to store n times n kernel matrix and compute a singularly decomposition SVD. Thus, RKPCA are not scalable to large-scale data. In addition, RKPCA has out-of-sample extension to reduce noise of the new data. Has no out-of-sample extension to reduce noise of the new data efficiently. So they improve on this here. So, robust dictionary learning. Classical dictionary learning and sparse coding algorithms, the noise by projecting onto the dictionary items. Dictionary matrix D and the sparse coefficient matrix C are found by solving, and then they have this minimization. The D is from SD, and yeah, so basically this minimization looks very similar to the original RPCA, except that the C, which is sort of the underlying latent matrix, is regularized here. There's no noise in the equation, and but it's looking for this linear transformation D. So the equation is effectively minimize 1/2 of norm of x minus d times c, or the d projection of c. So d projection of c needs to be close to the x in the Frobenius norm squared, plus lambda times L1 norm of c. So this is the regularization. So you're going for sufficiently small transformations such that well, actually, they're looking for sufficiently small matrix C such that the D transformation, which is the dictionary matrix, fixes it. Yeah, so basically dictionary matrix D and sparse coefficient matrix C, right? Okay. Contributions of the paper. Our contributions are threefold. First, we propose a new robust nonlinear matrix factorization model together, an effective optimization algorithm that explicitly separates sparse corruption of or outliers from the observed data. Second, we provide theory to prove correctness of our factorization in the feature space. Induced by kernels, and justify the use of squared Frobenius norm regularization of this feature matrix and coefficient matrix in factorization model. Finally, based on a robust nonlinear matrix factorization model, we propose new subspace clustering method. We validate the superiority of our proposed methods over baseline methods on synthetic data, and real image data, and real motion capture. Again, they use radial basis function. The remaining of this paper we focus on Gaussian RBF kernel because of following reason. First, we know we only need to determine the parameter sigma in Gaussian RBF kernel compared to two parameters C and Q in the polynomial kernel. Second, the Gaussian RBF kernel is easier to optimize, and parameter sigma controls the weights of low order features and high order features effectively. And so the problem they are dealing with is non-convex and non-smooth, and has three separable blocks of variables. We propose to initialize D randomly and initialize E with zeros, update C and D alternatively. In numerical results, we show that the alternating minimization always provides satisfactory dynamic performance, provided that the parameters such as lambda E are properly determined. Okay, I'm gonna go faster. So their time complexity, so compared to, they don't have the RKPCA here for some reason, but they compare to RPCA. So their time complexity is n. I think n is number of data points. It's, I think, dimensionality of the original matrix, and D will be this low dimensional matrix, I think. Okay, never mind. I haven't gone too deep on this one. So the conclusion: we have proposed new method called RNLMF to recover high rank matrices from sparse noise. We analyze the underlying meaning of the factorization loss and regularization terms in objective function. RNLMF can be used in robust dictionary learning, denoising, and clustering, and it's also scalable to large-scale data. Comparative is real and synthetic data and data verify the superiority of RNLMF. One interesting finding is that RNLMF reveals higher recovery accuracy compared to R. What was this norm? I forgot. This is the sum of absolute values of the singular values. And L1, the reason has been analyzed in section 8. It is possible that the sparse C given by RNLMF is more useful in sparse coding and base classification. Okay, and the results, again, they don't have the comparison with the previous method. That's really strange. Why wouldn't you have this? But the results they show, I think, are very good. For example, in case of occlusion, they effectively recover perfectly, basically perfectly, on the images of faces. Okay, so that's gonna be all. I hope you liked it. Let me know if you have any suggestions for future papers, and hope to see you next.